need to fix my wispies. Hold on. I got wispy issues. All right, anyway. I wanted to go over the practice for law of conservation of mass. So on this screen, it was just typing the words to finish out the statements, and you did have a answer key. And it would read, the law of conservation of mass states that matter cannot be created nor destroyed, only transferred from state to state. A balanced chemical equation proves the law of conservation of mass as it shows the same amount of atoms of an element and the reactants are also in the products. It's best to observe the law of conservation of mass in a closed system as it will ensure the mass is the same at the beginning and the end of a chemical reaction. So a closed system is like the video I showed you that's in week 7 of the balloon when I did the baking soda and vinegar trapped inside the beaker in the balloon. That's a closed system so that when the chemical reaction took place, no atoms were dispersed out into the room, lost into the air. They're not really lost, but we wouldn't be able to say 100% that the mass was the same if we couldn't contain it. Okay, so on the second slide, you're doing some drag and drop here. So looking at these looks like, above the H2 and the Cl2. Well, this part of the equation is known as the reactants, right? And that means that that side is the product. And this is above the arrow, and the arrow is a yield symbol. And then you would drag the other words. And if I think about it, this is showing me the chemical equation. These are the words I would say. 1 molecule of hydrogen gas reacts with 1 molecule of chlorine gas to yield 2 molecules of hydrochloric acid. So that would be the words. And then this is the model that shows that with our little blocks. Here, I'm looking at a scenario of silicon is the second most common element in Earth's crust. It's commonly used in semiconductors and electronics such as computers. Since it is naturally found in quartz, it is necessary to heat the quartz with carbon to separate the silicon. The chemical equation is SiO2 plus 2C yields Si plus TCO. 2CO. I haven't had lunch yet, guys. I'm hungry. All right. Which chemical formulas represent the reactants? Well, the reactants are on the left-hand side of a chemical equation. They're the two things that are going to react to create our new products over here. So I would just type in the chemical symbols. And I know it's like really small. Hold on. Let me make that bigger. Maybe I just delete and start over. Okay. But I would just type in the chemical symbols for that. There we go. Si or SiO2, excuse me, O2. And to do the subscript, there's a little tutorial here on the side, but you could just highlight it. And then on your keyboard, hit Control, comma, and it'll do it for you. Okay, so that I would type out the formula names for my reactants and then my products. And then I would count the atoms. How many do I have? Well, I have 1 silicon. And according to that, I have 2 oxygen, and I would continue. And then I would figure out, is this balanced or not? And I would know that if the exact same amount of silicon, oxygen, and carbon are on both sides of that equation. If they're not, if there's even 1 more carbon or 1 less carbon or any of them, then it's not balanced, because the law of conservation of mass says that matter cannot be created or destroyed, which means all my reactants have to also be in my products. Okay. On the next slide, you're doing basically the same thing. You're going to count your atoms. So here I would say hydrogen is 2 times 2 is 4. 2 O's is just 2. Over here, my coefficient of 2 must be applied to the hydrogen and the oxygen. So I'm going to say 2 times 2 hydrogen is 4, and 2 times 1 oxygen is 2. So yeah, that's balanced. I'm going to go ahead and do number 4. Okay, so 2 potassium, that's pretty simple. 2 chlorine molecules. So it's Cl2, but it's 2 of them. So really it's 2 times 2 is 4. This 2 in front of the potassium chloride, KCl, means that I'm going to multiply that 2 times my 1 chlorine, which means I have 2 chlorine. And that 2 times my 2 potassium, excuse me. I'm going to multiply that 2 times my K, my potassium, so that's 2 potassium. And then I'm also going to do the chlorine, 2 times 2. 2 times my chlorine is 2, because it's 1 Cl, but times 2. And that means that's not balanced, because those numbers are not the same. So I would drag that over to no, if it lets me. Okay, so I would drag it to no. All right, my little video box is in the way. So my own face is blocking me from dragging that to where I want to. This one, I am going to make my models. So this side is done for me. I can see my H2, but I've got 2 of them, 2 H2, and then my O2. So I have 4 hydrogen, and I have 2 oxygen, and then I have to build this model. So I'm going to build my H2O model first, because I'm going to forget this coefficient for the moment. So H2O would be 1 hydrogen, 2 oxygen, and they need to be touching because they're a compound, but I have 2 of them. So I have to build another one. Another one. So now I have 2 water molecules. And if I count up 1, 2, 3, 4, 5, 6, I have 6 total atoms, which makes sense because 4 plus 2 is 6. So I would do that for the rest of the slides. And then at the end, I have count the atoms on both sides of the equation. And it says show all your work. Your work is going to be over here in these little tables that I set up for you. So I have to start with my reactant side. So this is my reactant side right here. And I have 2 nitrogen and 3 times 2 hydrogen, so 6. Then I go to my product side, and that 2 coefficient is going to get multiplied by the nitrogen and by the hydrogen. So 1 nitrogen times 2 is 2, and 3 hydrogen times 2 is 6. So yeah, that's balanced. And I can prove my work right there. Over here, which of these is balanced? So I might need to use some scratch paper and kind of make my tables, or I guess I could even copy these tables if I wanted to and make enough of them so that I could go through all of these, and then I'm going to circle which letter is the balanced one. According to the law of conservation of mass, how many grams of hydrogen are needed for this reaction? So this is kind of like that idea of a closed system. I know that I started out with 2 hydrogen atoms that I added to an oxygen molecule, so they reacted to create this new product of 2 water molecules. And I had it on a scale, so I know that at the end, my product was weighed 40 grams. That was its mass. And on this side, the oxygen on its own had a mass of 15 grams. So then I'm kind of just figuring out, well, then how much was the mass of my hydrogen gas? And I can do that by just balancing it out, right? If it's 40 on one side, it has to be 40 on the other side. So do a little math, and I should be able to figure out like 40 minus 15 equals, and that should be my answer. Okay, I hope this was a little helpful. I know that it's maybe a little too late for some people, but even if it's just checking the work that you've done, then that's not a bad thing. We get to be able to do that. Hope you have a good day.